I'm Joe Flaherty. Last fall, a coworker gave me this directional gyro from World War II. The gimbal inside has the standard pitch and yaw rotations, but the flywheel is spun up by a compressed air source. Here's the intake back here. The air passes through this filter, then down in a tube into the base. Then it makes its way up into a series of holes in the first gimbal joint and into a nozzle aimed at the flywheel. I think it's amazing how engineers integrated the air system into this compact, rotating structure. This is an awesome piece of hardware, and it's fun to play around with, but I had to make a few changes before I had my new desk toy. Since the gyro was only designed to measure yaw, the flywheel's pitch is constrained from full rotation. Also, the top bar on the middle gimbal gets in the way if you try and spin it up by hand. Lastly, I don't have a good way of connecting an air source to the casing like the design intended. So I took the flywheel and its bearings, and I made this. This gyro still uses compressed air, but the plumbing is drastically simplified. Let's start at the air inlet, which fits a standard Schrader bike pump. Plastic tubing leads up to the first gimbal joint, where a hollow steel shaft sits in a long journal bearing. The air then reaches a T, passes through similar hollow shafts, and exits through nozzles aimed at the flywheel. Since I had originally planned to self-fund this project, cost was a significant constraint. Every part is either 3D printed, laser cut, or stock hardware. I have free access to a laser cutter, so I cut the whole structure out of a single sheet of acrylic. I had to pay for the printed parts, which were made on a Stratasys Objet. Its precision allowed me to build tiny cavities in my air system, but it can be prohibitively expensive to print in large volumes. I took many steps to keep the build volume down. The thickness of the elbows was dictated by the diameter of the journal bearing I'd chosen, plus a minimum wall thickness. The mounting holes are also squeezed tightly against the internal features to keep the footprint small. The T has no bearings inside it and could have been made slightly thinner. But the acrylic structure needed a flat surface to mount against, so I added the extra thickness with a thin bezel. The mounting holes were again integrated with the internal geometry. It all came together nicely, but my budget constraints did have consequences. Ideally, I would have used sealed ball bearings to keep my joints airtight. Instead, I had to make do with a leaky connection between plastic journal bearings and a loosely toleranced hollow shaft. The shaft tolerances also had consequences for the gyro's overall width. A shaft was pressed into either side of the inner gimbal, but their uncertain diameters forced me to lengthen the holes and ensure a snug fit. On the other side, I had to lengthen the journal bearing in an effort to lower air leakage and give myself room for error when I cut the shafts to length. The journal bearings also forced me to add thrust bearings on each shaft, adding more width. If I were to build a version 2, I'd invest in some better shafts and ball bearings to make it airtight and smaller. Then I'd come up with some graphics and etch it onto the black acrylic. Here's the final product running on shop air just minutes after I first assembled it. I hope you found this interesting. Thanks for watching.